Electrons in atoms do not orbit randomly, they occupy specific energy levels. When an electron transitions between these discrete states, it must conserve energy by emitting a photon. This process creates the light we observe from stars to neon signs. After that first surprise, we can slow down and trace the mechanism behind how atoms produce light. Energy levels explained from the first physical step, so the effect stops feeling mysterious and starts feeling engineered. To understand how atoms produce light, we must first establish the physical components of an atom without relying on outdated planetary models. At the center lies a dense nucleus composed of protons and neutrons, which contains nearly all the mass of the system. Surrounding this core is not a vacuum with orbiting particles, but rather a diffuse electron cloud defined by probability regions where electrons are likely to be found. Consider the contrast between a solar system model and quantum mechanical reality. While planets follow fixed paths, electrons exist in delocalized states governed by wave functions. This configuration creates the necessary conditions for energy exchange. When external forces interact with these charged particles within their specific spatial distributions, with the structural framework established, we can now examine how these electrons occupy specific quantized energy states that determine photon emission. Pause 0.8 to understand how atoms produce light. We must first establish that electrons do not orbit the nucleus at arbitrary distances. Instead, they occupy specific, discrete energy levels that function as non-negotiable constraints on their possible positions. Imagine a ladder, where each rung represents a fixed energy value with significant gaps between them. An electron can exist only on these rungs and cannot hover in the empty space between two steps. This contrasts sharply with classical intuition, which might suggest an object could slide smoothly up or down a slope at any height. In our atomic model, movement requires jumping from one rung to another, absorbing or releasing energy during that transition. Therefore, light emission occurs only when an electron drops from a higher rung to a lower one within this quantized structure. Now that we understand these allowed states, let us examine the lowest possible rung, where electrons naturally reside before excitation occurs. Pause 0.8 to understand how atoms produce light. We must first establish a reference point for electron energy. Every isolated atom possesses a specific lowest stable configuration known as the ground state. In this baseline condition, electrons occupy the innermost available orbitals closest to the nucleus without external influence. Think of this like a ball resting at the bottom of a valley where it remains until an outside force acts upon it. This stability is critical because any emission or absorption event requires a deviation from this equilibrium position. For example, in a hydrogen atom, the single electron resides in the first principal energy level designated as n equals 1. Attempting to describe light production without defining this resting state would be like measuring height without establishing sea level. We must recognize that the ground state represents the minimum potential energy configuration for any given atomic system. Once we establish this baseline, we can then examine how external forces disrupt this stability to initiate photon emission. Pause 0.8 to initiate light emission. We must first supply energy to the system from an external source. This input overcomes the natural stability of electrons in their ground state configuration. Thermal excitation occurs when kinetic particles collide with atoms and transfer momentum directly to bound electrons. Imagine a fast-moving gas molecule striking an atom, much like a billiard ball hitting another object on a table. The collision transfers sufficient energy to promote the electron into a higher orbital shell above its equilibrium position. Electrical excitation follows a similar principle but uses electric fields to accelerate free electrons toward target atoms. In both cases, the external input provides the necessary work required to bridge the energy gap between levels. Without this continuous supply of kinetic or electrical energy, the system remains in its lowest stable state. Once the electron occupies this elevated state, it becomes unstable and must eventually return to a lower energy configuration through relaxation pathways. Pause 0.8 When an electron occupies a higher energy level, it exists in a state of instability that naturally drives it toward equilibrium. This spontaneous return process occurs without external prompting as the system seeks its lowest possible energy configuration. Consider an electron initially excited to the third rung of the atomic energy ladder following thermal input from a previous stage. The particle will descend directly to the ground state or cascade through intermediate levels, depending on available quantum pathways. Each downward transition represents a discrete step, where potential energy converts into kinetic motion within the orbital structure. This mechanism differs fundamentally from stimulated emission, because it proceeds independently of incoming photon interactions. Visualizing this as an arrow moving down between specific rungs clarifies how quantized energy differences define possible routes. We now examine how this energy release manifests physically through photon generation during these transitions. Pause 0.8 When an excited electron relaxes back to its ground state, the atom must conserve energy by releasing the excess potential difference. This lost energy does not vanish, but transforms into a discrete packet of electromagnetic radiation known as a photon. Think of this process like a ball dropping from a shelf. The gravitational potential energy converts directly into kinetic motion and sound upon impact. Similarly, the electron's transition releases its stored energy as an oscillating electric and magnetic field propagating outward at light speed. The resulting waveform emerges precisely when the quantum jump completes, marking the birth of the emitted particle. Pause 0.8 The specific color of light emitted depends entirely on the precise energy difference between two electron orbitals. When an electron drops from a higher level to a lower one, it releases a photon whose frequency is directly proportional to that energy gap. This relationship means larger jumps produce shorter wavelengths, appearing as blue or violet light, while smaller transitions yield longer red wavelengths. Consider the hydrogen atom, where a transition between specific levels creates a distinct red line in the visible spectrum known as H-alpha. A slightly different jump within the same element results in green or blue lines, because the energy spacing is unique to that atomic structure. We visualize this correlation using a spectrum bar, where each color band maps directly to the distance of the electron's descent on an energy ladder. This unique mapping of energy gaps to specific colors allows us to identify elements by their light, leading directly into the concept of elemental spectral signatures. Pause 0.8 Every element possesses a unique set of electron energy levels, determined by its nuclear charge and orbital structure. When an excited electron transitions between these specific levels, it emits photons with frequencies corresponding exactly to the energy gap. This creates a distinct spectral signature that acts as a fingerprint for identification purposes in astrophysics and chemistry. Consider hydrogen, which displays 4 visible lines, while helium exhibits a more complex pattern due to its 2 electrons interacting differently. The precise arrangement of these emission lines allows scientists to determine elemental composition without physical sampling of distant stars. Pause 0.8 Atoms emit light through electron transitions between discrete energy levels. Excitation promotes electrons upward, while relaxation releases photons with specific wavelengths determined by the energy gap.